The sun, a blazing ball of plasma, a giant nuclear reactor in the sky, constantly churning out energy. It is the heart of our solar system, holding everything together with its immense gravity, ensuring the planets remain in their orbits. Without the sun, there would be no light, no warmth, no life on Earth. It is the source of all energy that sustains our planet. We are bound to this star, its destiny intertwined with our own, influencing every aspect of our existence. The Sun is classified as a G-type main sequence star, a category that includes stars in the prime of their life. This means it's in the prime of its life, steadily fusing hydrogen into helium in its core, a process that fuels its radiant energy. This process releases an incredible amount of energy, radiating outward into the solar system, reaching every corner of our planetary neighborhood. The Sun is about 149.6 million kilometers from Earth, a distance we call an astronomical unit, or AU, a fundamental measure in astronomy. Even at this distance, the Sun's energy is what drives our weather patterns, ocean currents, and allows life to flourish on our planet, making it a vital force in our daily lives. Understanding the Sun is not just about unraveling the mysteries of a celestial object, it's about comprehending the very essence of our existence. It's about understanding our place in the cosmos and the very forces that make our existence possible, connecting us to the universe in profound ways. The Sun might appear as a smooth, uniformly bright disk in the sky, but it's a dynamic and layered structure. We can divide the Sun into several distinct zones, each with its own unique characteristics. At the Sun's core, temperatures reach a staggering 15 million degrees Celsius. This extreme heat and pressure are where nuclear fusion takes place, the engine that powers the Sun. Moving outward, we encounter the radiative zone. In this dense region, energy generated in the core slowly travels outward in the form of photons. It takes hundreds of thousands of years for photons to navigate this zone due to constant collisions with particles. Next comes the convective zone, where hot plasma rises, cools, and sinks back down, much like boiling water in a pot. This process of convection transfers energy from the radiative zone to the Sun's visible surface. The Sun's immense energy output is generated by nuclear fusion occurring in its core. This process involves hydrogen atoms, under immense pressure and heat, fusing together to form helium. The mass difference between the original hydrogen atoms and the resulting helium atom is released as energy, according to Einstein's famous equation E equals mc squared. This energy is then carried outward from the core in the form of photons, units of light and heat. This fusion process is a balancing act between gravity pulling inward and the outward pressure from the energy released. This balance is what keeps the Sun stable and allows it to continue shining for billions of years. Every second, the Sun converts about 600 million tons of hydrogen into helium, releasing an unimaginable amount of energy into space. Only a tiny fraction of this energy reaches Earth, but it's enough to sustain all life on our planet. The Sun may seem constant, but it's a dynamic, ever-changing star. Its surface is a whirlwind of activity driven by powerful magnetic fields. One of the most noticeable features of solar activity is the appearance of sunspots, cooler, darker regions on the Sun's surface. These spots are caused by intense magnetic activity that inhibits the flow of heat from the Sun's interior. Sunspots are often associated with solar flares, sudden bursts of energy and radiation. These eruptions occur when magnetic field lines twist and snap, releasing tremendous amounts of energy. Solar flares can disrupt radio communications and even pose a risk to satellites and astronauts in space. Another dramatic display of solar activity is coronal mass ejections, or CMEs. These are massive eruptions of charged particles from the Sun's corona, the outermost layer of its atmosphere. Section 5. The Sun's breath, solar wind and its impact. The Sun doesn't just emit light and heat, it also releases a constant stream of charged particles called the solar wind. This wind is a result of the Sun's superheated corona, where particles have enough energy to escape the Sun's gravity and flow outward into space. The solar wind carries with it the Sun's magnetic field, creating a sort of magnetic bubble around the solar system called the heliosphere. This bubble acts as a shield, protecting us from harmful cosmic rays. When the solar wind reaches Earth, it interacts with our planet's magnetic field, creating beautiful auroras, also known as the northern and southern lights. However, Intense solar winds from events like CMEs can also disrupt satellites, communication systems, and even power grids on Earth. Understanding and predicting solar wind activity is crucial for protecting our technology and astronauts in space. Section 6. Sunspots, a window into the sun's magnetism. Sunspots, those dark blemishes on the sun's surface, are not just cosmetic features. They are fascinating phenomena that reveal much about the sun's inner workings. They serve as windows into the sun's complex and dynamic magnetic field, offering scientists a glimpse into the powerful forces at play. Sunspots appear darker because they are cooler than the surrounding photosphere, but they are still incredibly hot, with temperatures around 3,700 degrees Celsius. This contrast in temperature is what makes them stand out so distinctly. These spots are formed when areas of intense magnetic activity rise up from the sun's interior and break through the surface. This process is a key aspect of solar dynamics. The magnetic field lines in these regions are twisted and tangled, inhibiting the normal flow of heat and light from below. This magnetic tension is what causes the sunspots to form and persist. Sunspots tend to appear in pairs, with each spot having an opposite magnetic polarity, much like the poles of a magnet. This pairing is a direct result of the sun's magnetic field. The number of sunspots visible on the sun's surface waxes and wanes over an 11-year cycle, known as the solar cycle. This cycle is crucial for understanding solar activity and its impact on space weather. During solar maximum, the peak of the cycle, the sun is peppered with sunspots, and solar activity like flares and CMEs is more frequent. This period is marked by heightened solar phenomena. Conversely, during solar minimum, the sun's face is relatively spotless, and solar activity is subdued. This quieter phase provides a stark contrast to the bustling activity of solar maximum. Section 7. The sun's journey through time life cycle of a star. Like all stars, the sun has a finite lifespan. It was born from a cloud of gas and dust, known as a solar nebula, which collapsed under its own gravity. It's currently about 4.6 billion years old and is considered to be in its main sequence phase, where it will spend the majority of its life. This phase is characterized by the stable fusion of hydrogen atoms into helium in the sun's core. During this phase, it will continue to fuse hydrogen into helium in its core, providing a stable source of energy for billions of years to come. This process releases an immense amount of energy, which we perceive as sunlight. However, in about 5 billion years, the sun will exhaust the hydrogen in its core. This marks the beginning of the end for our star. As this happens, the core will contract and heat up, causing the outer layers of the sun to expand dramatically. This expansion will be so vast that it will transform the sun into a red giant. The sun will transform into a red giant, engulfing the orbits of Mercury and Venus, and possibly even Earth. This phase will be short-lived compared to the main sequence. As the red giant phase progresses, the sun will begin fusing helium into heavier elements in its core. This process will create elements like carbon and oxygen. Eventually, the outer layers of the red giant will be blown away, leaving behind a hot, dense core known as a white dwarf. This remnant will be incredibly dense, with a mass comparable to the sun, but a volume similar to Earth. The white dwarf will slowly cool over billions of years, eventually fading into a black dwarf. This cooling process will take so long that no black dwarfs are thought to exist yet in the universe. This is the final stage of the sun's life cycle, a cold, dark remnant of a once mighty star. The journey from a bright young star to a black dwarf is a testament to the dynamic and ever-changing nature of the cosmos. Section 8. The sun's influence on Earth's climate. The sun is the primary driver of Earth's climate system. Its energy warms our planet, powers our weather patterns, and drives ocean currents. The amount of solar radiation Earth receives varies depending on factors like Earth's tilt in orbit, leading to seasons. While the sun's energy output is relatively stable, even slight variations can have a noticeable impact on Earth's climate over long periods. Scientists study past climate changes to understand the sun's role in shaping Earth's environment. For example, periods of low solar activity, such as the Maunder minimum in the 17th century, coincided with colder temperatures in Europe and North America, suggesting a link between solar activity and regional climate variability. Understanding the complex interplay between solar activity, Earth's atmosphere, and other factors is crucial for predicting future climate trends and mitigating the potential impacts of climate change. Section 9. Conclusion: our star, our future. The sun, our local star, is more than just a celestial object, it's the lifeblood of our solar system. Its immense energy drives our weather, sustains life, and shapes our planet's environment. From the nuclear fusion in its core to the dynamic activity on its surface, the sun is a fascinating object of study, offering insights into the processes that govern stars and their evolution. As we continue to explore the cosmos, we gain a deeper appreciation for the delicate balance that allows life to flourish on our planet. Understanding the sun is not just about unraveling the mysteries of a star, it's about understanding our place in the universe and safeguarding the future of life as we know it.